Okay, let's look at problem 916 in the book. It's this kind of funny shape, and it says determine the moment of inertia and the radius of gyration of the shaded area with respect to the x-axis. So again, we're doing it with respect to this axis right here. Okay, lovely. So what do we have? Well, we have this area that's made up of this kind of two separate curves. So the obvious thing to do would be to, hey, let's create this little differential strip, right? So let's define this differential strip. dA is going to be the top curve, right, minus the bottom curve. So it's going to be y2 minus y1, all that times that thickness. Okay, so that's lovely, and that's a true statement, but it is not helpful yet for what we're doing. And why is that? Because when we do a differential strip, so say we have, let's come over here and the stuff we've done up to this point, we have some curve here, right? And so we'll say dA is equals y dx. But when we do the ix, it's integral of y squared dA, right? But we don't, this is a true statement, but it is not particularly helpful because we're not holding y constant for this strip. So instead, what have we done? We've said, well, also the differential ix is integral of 1/3 base times height, so dxy cubed. But where does this come from? This comes from a rectangle based on a rectangle based on this axis right here. And so if you look at this differential strip, come back over here, this differential strip is no longer on this one here. So you can't just use that. So instead, we're going to say this differential strip consists of this, I'm going to draw this, extend out, this whole differential strip to here minus this portion under here. And the advantage of this is these are both based on this axis. And so this 1/3 bh cubed bit will work for this problem. And that's the key to this one, is doing that. So therefore, what do we have? We have dix is, sorry my pen's being a little funny, it's 1/3 base, which is going to be dx, times this one, which is y2 cubed, minus 1/3 dx times the height of this one, which is y1 cubed. Okay, so now we have to figure out, these k's are going to be problematic, so we have to figure out what those are. So let's look over here. So y2 at a is equal to b, so it's equal to k2 times a to the 1/2, therefore k2 equals b over a to the 1/2. And y1 at a is equal to b, which is equal to k1 times a squared. So k1 equals b over a squared. Okay, so let's come back over here. So we have 1/3 y2, which is going to be k2, so b over square root of a times x to the 1/2. That's one thing. Now that's y cubed dx minus 1/3 y1, which is going to be x1, so sorry, k1, b over a squared x squared cubed dx. Okay, this is all equal to dix. So let's integrate both sides. So we have ix is the integral, and our integration limit, since we're doing a vertical strip, is going to go from here, and it's going to come across to here. So from 0 to a of 1/3 b over a to the 1/2. Sorry, I keep on switching between those. Actually, now let's do this a little different. Let's go ahead and cube this out. So b cubed over a to the 3/2 x to the 3/2 minus 1/3 b cubed over a to the 6 x to the 6, all this times dx. So therefore we can pull out the 1/3. So it's 1/3, and let's do this. Yeah, we'll just do each one individually. 1/3 times, that's going to be 3/2, so it's going to be 5/2, so it's 2/5 b cubed over a to the 3/2 x to the 5/2 minus 1/3 times 1/7 b cubed over a to the 6 x to the 7th. It's a 7. Pen struggling from 0 to a. Okay, so that works out to be, after a little bit of creative math, 2/15 times a b cubed minus 121 a b cubed. So therefore Ix is equal to 3/35 a b cubed. That is your second moment with respect to the x-axis. So again, the key here being that you can't do 1/3. Now, what we just talked about, you can't just go through and do this strip directly. You have to do the two individual strips because we're basing it all on this, which comes actually from the parallel axis theorem, and it's based on it being on this bottom strip. If you were willing to go through and figure out all the work for it to be some other location, that would be acceptable, but it would just be unnecessarily difficult. Okay, so that is Ix, but that is not all that they asked for. Now we have to do the radius of gyration. So what is the radius of gyration? K is square root of Kx, right? Is square root of Ix over area. So we have Ix. Do we have the area? We do not. But we can figure it out, and that comes down to what we did up here. We said it wasn't useful yet, but now is when we need to do that. Because that is the dA, so let's go through and let's integrate that. So therefore, integral of dA is the area, right? So that's integral of y2, which is going to be k2, so b over a to the 1/2 times x to the 1/2 minus y1, which is b over a squared, x squared, boom, dx from 0 to a. Okay, so then that's b over a to the 1/2 times 2/3 x to the 3/2 minus b over a squared times 1/3 x cubed. Evaluate this from 0 to a, so you end up with 2/3 ab minus 1/3 ab. So area equals 1/3 ab. Lovely. Therefore, kx is square root of 3/35 ab cubed over 1/3 ab. The square root's over the whole thing. So the a's cancel, obviously. The b goes to squared. So therefore, kx is equal to, I can pull the b squared, and quite frankly the 9, so 3b over square root of 35. And that is your radius of gyration. And that is the problem.